It is pretty neat, and you can see it moves the entire thing around when it spins, which is cool. So, hey everyone. No, I haven't made a video in just a minute. That's because I had a pretty big failure. But I'm not talking about that today. I'm talking about this today, and then I'm gonna film the next video. Is gonna be that. It's gonna be all about that. And those I'm gonna film today too, and those will be released within a couple days of each other. So we're gonna talk about the failure and how that's a pretty big part of my process and learning from it, but that's pretty much all I'm gonna try to say on that in this video, because on this video, we're focusing on this thing right here. So this thing is called the unit, and this is the unit of the ElectroHydraulic Actuator. So in this is a reservoir, a pump, a motor, and a control system, and then the actuator comes off of here. So we're not talking about the actuator at all today, we're just talking about the unit. So let's dig in, let's not talk anymore. So. All right, guys, so here we are. This is the unit right here. So it's all 3D printed chassis, and then I obviously, well, maybe not obviously, but a lot of these parts that were machined, I didn't machine. So I did some machining on this, but this right here, I didn't build this. This is a hydraulic pump off of I think an old, I think it was built for an old power steering column. This is a Brushless DC Motor, which we're going to talk about. This one's from Hobby King. This one is made for airplanes. They also use this particular motor in a lot of electric skateboards, or at least they used to. There's becoming a market and industry for motors made specifically for electric skateboards, but that's what that is right here. And then in here we have the electronics. This whole house is something called an ODrive, and then an Arduino. And then this right here is the encoder going into the ODrive. We're going to talk about all this in a second. So let's see, where do we want to start here? Let me talk first about this thing right here. So this is the reservoir. So it got larger. Ooh, I have some video of that being filled. I probably am going to switch to some video of this being filmed. I'm not sure if I'm going to do it right now, but let me explain it first, and then I'll switch to the video I have of it being filled. How about we do that? So this right here is the reservoir. So this is a clear piece of PVC. I wanted to upgrade this to another piece of polycarbonate at some point, so it's more optically pure, just for just to look nicer. Really, I believe in having a nice looking product. This product is pretty nice looking. That's what I like to do. It's important to me. So what happens is this is a pressure vessel, and then I put in about 30 psi of pressure into this tube above atmospheric, and then there's a in-buna rubber tube, which is the same thing that's on the inside of my actuators. So that's in there, and then there's a plug on this end. If you can see, I'm not sure, but there's a plug on this end of the tube, and that was super glued in with sacrocyanide, so just normal super glue essentially. And then same thing on this end, except this end right here, this part was, so these are the two machine parts in this. This part right here has got the nipple, and then this is bound in here, and this comes in here and goes into the pump, and then this is where the filling goes right here, the filler, which I'm going to show in a second. But so the pressure comes into here, and then it squeezes on this tube. So you can see, if you look at it right now, it kind of looks like it's being pressed, and it's leaky. It doesn't work all that well. So if we were to put this on a system, we need something to keep replacing the air with. We need a compressor on it, essentially kind of how airplane cabins work, or we need to get rid of the air compression system altogether. And the latter is probably more likely. What will probably be happening is this will be like a tube filled with oil, and also be a little bit more size efficient, I think, too. But this would be oil, and then there'd be a floating piston in here. So a piston that has a seal that the oil can't get through, and then a spring. So the spring will always be adding constant pressure, and there's no way to have it leak out your air pressure and have your actuator not work. But the entire point of doing all this is that when you press the air into this, it squeezes that rubber reservoir. So the reservoir is that rubber part, squeezes that rubber reservoir, and then you can turn this around and you can move it around in any orientation, and it'll always be pushing, there'll always be a positive pressure of oil going into the pump. So the pump can work in any orientation. So important if you're not putting these things on ground-based things. So since this is trying to be an Iron Man suit, it needs to work in any orientation, because you move your arms around, you're flying, whatever. And then if it's going to work on in aerospace, it also needs to work there. And I've had Lockheed Martin has reached out to me, and they are interested in this technology, so they say. Working with big government companies is weird. It's slow. That's what it is. But anyway, so yeah, that's the reservoir. So now what I'm going to do is I'm going to switch real quick to the garage, and I'm going to show you how this is filled. I have a blooper from there, which is pretty funny too, but I'm going to switch over and do that. So boom. Hey, so I decided to post this as its own video. It's pretty funny, so you should watch it in the link below. I'm going to switch over and I'm going to start taking this thing apart. So I'm going to start with showing you, I'm going to take this part off first. So in this compartment right here is a 9-volt battery, and this unscrews here, and the battery just sits down inside there, and then there's a hole bringing the power in. So now I'm going to unscrew this and show you what it looks like on the inside here. Oh, I want to show this real quick. I took one of the screws off, but here, this is the on-off switch. I labeled it because I like my systems to be robust, so this way you actually know. And for a while, the light came on, so for a while I didn't have that, and that was just confusing, so I went and added those on there. So anyway. So I don't know if you can tell in the sped up version of that, but this is not a very efficient way to do this. What I did is I glued the screws in, and then I put the bolts on. This is a poor way to do things if you're 3D printing stuff. This is all 3D printed, by the way, or all the black is anyway. If you're gonna do something like this, glue in your bolt, or your nut rather, and then put your bolts in. Works a lot better. So what you want to do is you want to put into your CAD design a hexagon in there, and then you with a little oversized, and you press it in with some super glue, and it doesn't go anywhere. Works really well. These get bent. These are hard to screw on. Doesn't work very well. I hope that lighting is okay. All right, I adjusted the lighting a little bit, so I hope that helps you guys see this a little bit better, what I'm doing. So now I'm going to open it up. So in here, we have the electronics. So not the ugliest stuff I've ever made, not the prettiest either. So in there, you can see I have something called an ODrive. So this is an open source board that I'm gonna talk about in a second, but I just want you to look at it really quick. And then in here, this snakes around and plugs into it. This is the encoder that this thing works off of. And then there's 3 wires coming off the Arduino over here that tells this thing what to do. So this thing is in charge of moving the motor, and then this is what I actually communicate with, which with the other part of this thing, which I actually haven't showed you yet, which is this remote. So this remote plugs in right here. So if this was on, it would plug in right into here, and then I just desoldered a USB thing, and then this is a USB off of Amazon, and so that just goes right in there like that, and that's how I actually control this entire thing, is with this remote right here. So there we go. So let's, there's also some fans in here. Those ended up not even really using those, but the idea was they would blow on where the FETs are to actually control this thing. So let's talk about the ODrive real quick. So those will be one of my kind of basic review of the ODrive. So that's this thing in here, which you're probably not able to see from the lighting, but I'm just going to talk about it for a second. So this is the power into that, by the way. This plugs in here. I am going to spin this thing up at the end, and and show you how it actually works. But so this thing right here is what's called what this open source board does is invented by a guy named Oscar. He's a pretty nice guy. I've talked to him quite a bit actually while troubleshooting on this board, and he's helped me out, and he's a pretty good guy. What he's done is he's taken this need in industry, in the robotics industry. So CNCs and big industrial robots, if they move fast, they don't use stepper motors. If you're familiar with what a stepper motor is a bunch of teeth, and they move like this, and you can put the voltage in and change it, and they move a certain step each time. And so what you essentially, they move with enough reliability and enough accuracy that they don't need any kind of feedback system to tell you where the position of the motor actually is, as long as you're not moving them very quickly. So as long as you're moving them at slow speeds, they move very accurately. The problem is if you want a lot of power out of your tools, or if you want them to move quickly, so for industry, that's important. You can't use stepper motors because they start to lose step after certain velocities. they're nice because they're easy to use and easy to implement, but they don't have a lot of power. So that's where these motors do. These are the same kind of motor that's in the much smaller version of this is in the Model 3, Tesla Model 3. So essentially what this does is this thing right here is an encoder. So this thing will tell how, and it's got, so essentially what it does is it tells it where it is, and for every single turn there's 8,192 encoder counts per revolution, I think. So that is how many, so it can tell with a really high degree of accuracy where this motor is. And so then this cable comes into here and plugs into this, and then this thing knows where the motor is and can move this motor that can now move very quickly and with a lot of power, also with a very high degree of precision. Now, for my use, this is not probably the best setup. So if you're just driving directly a shaft or something, a rigid body, it works because there's no slip. The problem with a hydraulic system is that there's slip in the system. There's oil that leaks back through. So if I pump this thing up and I move it, X distance, and I think it's gone X distance based on the encoder, well, the oil can slip, and now I'm, at 1.1 X distance, or I'm at 0.8 X distance because the oil is slipping around. And so what I really need is something more like a speed controller in this. So I ended up starting with this, thinking this was going to be a good idea, and then I had some issues with the board, which I'm going to talk about. And then realizing this was probably not necessarily the best thing for me to work with. So what I did instead is, unfortunately, I'm not going to be able to show this too much, but there is a string on the actuator that spins a potentiometer that's on the actuator, and then that potentiometer gets plugged into this over here, and I'm going to show you underneath so you'll see how this is routed through. But it plugs in here and then routes up through the chassis here and then comes up with this braided wire right here and plugs in to the Arduino. And then that way the Arduino can measure the position of the actuator, or the exomuscle, where it is with a good degree of accuracy. And the nice thing about using an analog system, which a potentiometer is an analog system, is that you don't have to calibrate it at all. You just get a resistance across it and you know where it is. So as long as you're not pulling on that position sensor or something like that, you will know the position always. Even if the system has to reboot or something and come back up, you'll always immediately have that position. So you don't have to do any kind of calibration in order to get it to work. So that's a good, useful thing with a analog. So that is how I'm actually measuring the position of the actuator, is not through this encoder, but through this. So it makes this encoder a little bit superfluous because I'm only using this thing in speed control mode, which is important. If you have something like the spindle on a CNC, you need to know exactly how fast it's spinning, because that has to do with your chip load and stuff and how much material you're hogging off or removing and what the tool can take. So it's important for stuff like that. The velocity probably doesn't need to be that specific for what I'm doing. So this may end up, even though I think this is a good thing he's doing, I think it's a little overkill for what I'm doing, and what I need is something actually, I think, to be as responsive as possible, because when you're in an exoskeleton, you want the skeleton has to respond to your movement very, very rapidly. So we want a very responsive system, in something that doesn't in a powerful system, but not necessarily something that has to be super, super precise in its motion, because there can be quite a few revolutions before, and that's only going to move the actuator just a little bit. So that's kind of how that works. Overall, I think this is a good product. One issue I did have with it too is that I can't spin it up to full velocity, and I'm working with Oscar on that right now. We're looking at trying to get that figured out. But for me, higher speed and power and responsiveness is probably more important than really high precision in the movement. But the reason I did this is I was getting ready for a conference, and then the failure happened, which I'm going to talk about in the next video, and I ended up not going. But I had this board sitting around, and I really couldn't afford to get another board in here, so I ended up just taking this and trying to make it work, and it was working. It was the actuator that failed. So yeah, this is the inside. This is the guts. This is the electronics of the system. This Arduino, these are all soldered to a PCB board. It's not a great I didn't do a very good solder job on this. There's a mess of wires in here. So this part is kind of ugly, but it gets tucked in and looks okay. So, oh, one thing I want to talk about really quick. These connectors right here, this is the connector for the potentiometer, the linear position sensor that I built for the actuator. I glued on to these things just pieces of plastic, and that keeps them, these are DuPont clips, but that keeps them from being able to go together the wrong way. So this is what I call a robust system. I like robust systems because they're very important to me, because I want a system to work as well as it can. I want it to essentially be not fuck upable is what I want. So this makes it, and there's also another one on where you plug it in, and those are the two connections. It makes it to where you can't plug this in the wrong way, because you plug it in, you get if you plug it in the wrong way, you get an inverse of the data, and it moves opposite the direction you're expecting it to move. So it can mess up where your linear position, it makes it to where it doesn't work, essentially. So I like robust systems. So that's something I'm always striving for, is to make a system as robust as possible. So I try to do that in hardware, and I also try to do that in software. So I do that on both fronts there. So I like systems to be robust. So this is something I'm always doing and I'm always looking for. And another example of the robust system is that this right here, this Reservoir, it used to be a lot smaller, and it was just enough fluid to fill and contract the actuator, but it couldn't take the fluid back in if it got stuck in reverse. There was supposed to be a sensor that kept it from going in reverse and overfilling the reservoir, and my software that I wrote for that didn't work, and this thing got stuck on and reversed itself, filled up the smaller reservoir and ruptured it. So wasn't a robust system. So I switched to a larger reservoir that I then pulled all the fluid out of the actuator. So vacuumed all the fluid out of the actuator, filled this thing fully, and then put the fluid in. So I knew that if this got reversed and I sucked all the fluid out of the actuator, this could handle that fluid. So again, a robust system in that regard. So now I'm going to put this back on, and then I'm going to show you guys the underside real quick and the chassis, and then that's about it after that. So that went on pretty well this time, but lots of times I have trouble getting those bolts on. So now what I'm going to do is I'm going to open this up real quick and let you guys see the underside of this. A little bit less going on this side, but I'll show it to you as well. Again, this was put on with that rather poor design of the screws. I've decided I'm never going to do this again, but this is how I designed this initial part. I'll always put in the bolts next time. So it's essentially like if you were doing a machine job, it would be like machining in threads just right into your part. You can't do that with plastic, obviously. 3D printed, not enough resolution, not strong enough, but you can glue in a bolt or a nut rather, and then you want to not glue in your bolt like I did, and then you want to put your bolts in. So that is done with it. I'll show you this too. So the way this hooks on to the to a pipe, the stand that I made, which I'll actually, let me go ahead and I'm going to cut to that right now. So I'm going to cut to this and how it goes onto the stand and the demo stand. I'm going to show you the demo stand too. So I'm going to cut to that. All right, I'm filming this real quick so you guys can see the stand I built. So there's the unit down there, and then the actuator would be plugged in right here, and then the sensor for the actuator plugged in right there. And then this is the reservoir. So I'm explaining this upstairs, but I want to show you this, guys, real quick. I want to build a badass carbon fiber one of these ones, because this is supposed to designed to be a traveling stand. It pins apart right here and comes out. So the muscle goes down into here, it locks on to this point right here, and then locked in here, and then you pull on this, and you see even if I pull pretty hard, it's hard to get up. So that's why you need like 5 tons of force to lift something way out here. And then I had some weight going on here. At one point the idea was to lift myself, but then I wasn't producing quite enough force with the unit to do that. So I switched to putting weight on it, and I was lifting 45 pounds off the ground really easy when the actuator broke. So I added this kind of extra piece down here to make it a wider base, like a foot. It's not the greatest designed stand, but it works, and it all pins apart. These pins come out here, and it all would fit in a suitcase. And actually I have traveled with it in a suitcase before when I went to New Orleans once, but I just want to show you guys that really quick before I took this stuff downstairs and put it on my desk and showed you. So there you go. Okay, and now that we're back from that, you can see here what I'm talking about with the bolts in the nut. So this right here, if you look there, this is the bolt coming out, and this is the hex right here, and this is the nut that was pressed into the 3D print and then glued on there. So that went on like that, and then so there, and then these screws came up to there. So okay, here, so we got the screws off, and then so I'll pop this off right here, like that, and then here you can see this is where that the sensor, the position sensor, linear position sensor for the actuator comes in, and this braided cable is piped around the chassis here, and then drilled in here, and these two bolts hold on the cover for all the electronics, and then these two bolts are holding on the pump, and then these 4 bolts are holding on the motor. And then here we have a pulley system. These are used to drive like 3D printers and CNCs and stuff like that a lot, and they're tooth pulleys so they don't slip. They work pretty well. This is a metal pulley that I got off Master Car, I think. And then the outside was machined down, and then I had to re-bore out, and then so I put it on a I think they call it a spindle, or I can't remember the name. It starts with a D, but so I put it on there and I clamped it down, and then I trued up the outside, and then I clamped it into the forejaw, and then rebored out the inside because I couldn't find a pulley in this size to fit this diameter motor I had, so I had to re-drill that out, and then I put it in with set screws. And this one right here has a keyway on it, and this one right here is 3D printed. This actually works pretty well. There's a guy who makes electric bicycles that had 3D printed parts on it. And I can't remember his name right now, but if you look up his YouTube channel, if you type in 3D printed electric bike pulley, you'll come up with this guy. It's a guy in England. He's got red hair. But anyway, he does that. And so this has more than enough force, strength to do that. It probably would even in here if there was a keyway, but there's not a keyway, so I needed set screws to hold that on. So that's the bottom there. And yeah, that's pretty much the entire thing. I think I've shown you guys everything on that. There's a cover here so the oil doesn't come out, because as you've guessed, I probably learned this from experience. If you push this thing, oil comes out everywhere, so I was really not liking that, so I 3D printed a cover on here. Again, kind of back to those robust designs. I like robust designs that work well. So that's it. So now what I'm going to do is I'm going to put it back together, and I'm going to fire it up, and I'm going to show you this spinning. I have to take the pulley off first because this isn't attached to the actuator right now, and it'll increase the pressure in here really high. But I actually am going to show you this spinning really quick because I think that'll be fun. So let's go ahead and do that. All right, so I got the pulley off, got the window back open because I missed the natural light. So now we're going to go through the startup sequence on this. So first thing I do, plug it in, you'll see a spark. I'm not really sure how to get rid of that. And then I'm going to do is I'm going to turn it on, and it'll move. It moves just very slightly, and it's going to beep. And it's going to spin. And so this is what I was talking about, calibration. So when you use a system like this, it has to calibrate. So it has to spin until it finds the Z index on that, and then do it that way. So now that that's on, we got to plug this in. So this, let me show you the batteries really quick. This is a 2 5-cells pulled together into a 10-cell. So you can buy these online. I just made this one, soldered these together. These batteries are lithium polymer batteries. They're really high discharge rates and energy storage. Actually, better than the batteries that they put in Teslas. They're a lot more expensive though. That's why they don't put these kind of batteries in Teslas. Tesla batteries are good, but these are a little better. They're also hard to cool. I mean, there's pros and cons to them. Mostly the price is the con though, with something like that. So now this is on. Turn this on. This also has a battery in here. There's also an Arduino in here, and then these two are talking through the serial communication to each other. So we just moved. There we go. So and then so this right here adjusts velocity. So you can see it's moving really slow there. This right here adjusts the amount of amperage it lets the system run at. So I can run harder this way. So then faster. So now if we move up to a higher speed, we might see the problem I was talking about. What happens is this motor, when it spins up, it has rotational inertia that is trapped in it. So when it speeds up and it stops like that, that rotational inertia, it has to go somewhere. And so what happens is when it stops it, this turns into a generator. You can essentially, you could run these with a gas engine. You can make a generator out of these motors. So anyway, that it acts as a generator for a second and turns that rotational inertia into an amperage spike, and this board has trouble dealing with that amperage spike. I'm speaking with Oscar, the maker. He's talking about sending me another board to test to see if it works. I tried his new firmware update. It didn't seem to fix the issue, so he might be sending me a new version of his board. Seems to be working on the project pretty actively, which is cool. So anyway, we'll see if that happens. So it spins pretty fast. Now this is only this is less than half the speed this thing can run at full speed. So these motors are really fast. That's why they're amazing motors. That's why if you've ever driven a Tesla, it's like, whoa, it's like driving a spaceship. That's kind of how these motors are, and that's why we want them, but they're still not spinning at the full speed. So spin it at full speed, see if we can get this thing to kick off. So pretty fast there. It is pretty neat, and you can see it moves the entire thing around when it spins, which is cool. So there it is. So it kicked off right there. So that's what happens with the amperage spike right there. I may even send this video to Oscar and let him look at it. But that's what happens with that. So so that's pretty much the entire thing. So all right, everyone, thanks for watching. I really, I put a lot of work into this particular system, and the actuator failed. This system actually worked fairly well. This has got a long way to come. One thing I got to do in the future is I'm going to build a board, I think, from scratch. I think that's really the only way to do it. All the 3D printed parts eventually need to be machined. The pump has to get a lot smaller. The reservoir needs to be improved. There's a lot of stuff that needs to be changed. These things need to get a lot smaller and a lot tighter if they're going to go in an Iron Man suit and be efficient, because this is way too large to actually work. But I hope you guys think that's cool. It took me a lot of work. I put a lot of time in this. I put a lot of time to make sure it looked really good. I put a lot of time in to make sure it functions. I rebuilt the reservoir like 5 times, I think. So there's a lot of work that went into it. If you like what I'm doing, do me a favor and please subscribe. Right now I'm doing pretty good on the YouTube channel. The YouTube channel is small right now, and I'm doing pretty good on my watch time. Right now I don't have hardly any subscribers. So if you like what I'm doing, there's more videos to come. So please hit subscribe, hit the little bell notification too, and we'll see you soon. Thanks.